Hi everyone, thank you for attending my talk. My name is Ray and I'm from Dr. Gopalan's group at Penn State University. Today my topic is anisotropic optical properties in Walls and metal. This work is supported by MERSAC and is accomplished with collaboration with Transfer Group at Penn State University, Theory Group at Southern University of Science and Technology and Northwestern University, and Synthesis Group at UCLA. Although Wolframion was initially predicted in a high-energy physics, it was first experimentally discovered in condensed matter, namely the tandem arsenic family. Wolframion can be described as a low-energy excitation near the crossing point of singly degenerate atoms in the presence of broken inversion symmetry or broken time reversal symmetry. In the tandem arsenic family, the inversion symmetry is intrinsically broken, leading to a non-central symmetric structure. Optical transition near wall points have been identified as shown in the right panel. Two linear band crossing can be observed as highlighted by the dark circle. The optical transition for tandem arsenide between saddle points have been identified as well. Optical measurements have been used as a powerful technique to characterize the exotic properties of walls and metal states. The linear optical conductivity near wall points have been explored. Two linear slopes were previously studied, indicating linear bands for two different types of optics. In addition to the linear optical phenomena, giant nonlinear optical response, namely second harmonic generation, was also studied. The giant SAG response in the tandem arsenic family have been attributed to the shape curves and nonlinear resonance. While extensive studies have focused on optical transition near wall points and possible reasons that contribute to that giant SAG, the anisotropic optical susceptibility and then a momentum result optical transition is some reasons. To that end, we present the complete anisotropic property of and discuss the consequences of anisotropy in utilizing the optical probes for probing wall physics. Firstly, the dielectric function of one direction probed by the spectrometry is shown. Next, the dielectric function calculated by the DFT is included. The experiment and DFT is also agreement in terms of position and magnitude. The level of DFT and experiment is considered acceptable because DFT is a zero Kelvin theory and has a well-known underestimation of the energy of exciting state. Similarly, the dielectric function along 3-3 direction are shown in the following panel. Here, the epsilon 1,1 and 3-3 are the tensor components of a uniaxial structure as shown to the right, where 1,1 is along the crystallographic A or B axis, and 3-3 is along the crystallographic C axis. Next, we look into the macroscopic resonance and conduct the fitting of the dielectric function using Lorentz oscillator and Joule response. Firstly, the total imaginary dielectric function obtained by experiment and DFT are shown. And the fitting equation is shown at the right. Here we focus on the Lorentz resonance and Joule response, which corresponds to the second term and third term of the equation. The first broad resonance shown in blue is a resonance at 2.9 eV. The second resonance colored in purple shows resonance at 4.8 eV. Followed by two resonances are high energy as colored in orange. Similarly, the rest of the resonances can be obtained as indicated by different colors. The Joule response is also included in the spectrum, and this shows a strong response below 0.2 eV as shown in the DFT. With the confidence in the DFT calculated dielectric function based on its reasonable comparison with experiments, we next investigate their microscopic arrangement and possible enhancement of the giant SAG. In the figure to the left, the calculated band structure and the resulting density states for tandem arsenide are shown. The colored band corresponds to the percentage of tandem d orbital as compared to the tandem d orbital and arsenide d orbital. Well points are highlighted in the dashed box in the absence of the spin orbital complex. The zoomed-in band structure of the dash region is further shown to the right. Due to the spin orbital coupling, the gap are open between the cone. The position of wall points are further highlighted in the dark rectangles. Furthermore, the optical transition near wall points are mostly tandem 5D to tandem 5D transition, and are
no biting.
To look at the microscopic arrangement of those resonances, the bands are sequentially numbered C1 to 8 and C1 to 8, as shown in the left panel, to help to identify the optical condition. The origin of those resonances can be reviewed by utilizing the transition dipole matrix element. And therefore, the dielectric function can be viewed as a function of photon energy, which is shown in the axis below, and the momentum space, and which is axis to the right, and certain pairs of band, which is colored in the legend. This color legend represents the selected pairs of bands that exhibit major contribution to the dielectric function. At energy below 1 eV, 3 dominating bands can be observed. Those are V1 to C2, V2 to C1, and V1 to C1 transition. Major optical transition and energy where giant second harmonic generation was observed are also evaluated. At 0.7 eV, the dark arrow depicts the parallel bands between V1 and C1, and it provides dominant contribution to the dielectric function. We also found Van Hoek singularity exists, which increased the joint density of state, which promotes more optical transition. At 1.55 eV, the dominant contribution remains to be V1C1. Similarly, at 3.1 eV, the giant second harmonic generation is enhanced by a collection of bands mostly concentrated at high symmetry point Z. And that's why it contributes to both passives as shown in the panel. And those are also enhanced by the Van Hoek singularity as well. Motivated by the resonances near the well point, we then examine the contribution of momentum space in the proximity of 2 different well points to the dielectric function. Looking at the schematic of the well point as presented to the left, the well point resides at a certain momentum space, as you can see, which is as a function of the K. We then perform the dielectric function calculation in a small K space in the proximity of well point with a small volume of the K space in the first Brillouin zone. And those K space size is about 0.01 to 5% of the first Brillouin zone. The contribution to the dielectric function near well point are then demonstrated in the right panel. Firstly, the total dielectric function including the Joule response is shown. The contribution from well point 2 is colored in blue, followed by the red regions that are contributed by the well point 1. Finally, we consider the free carrier response as colored in yellow. The region between total response and the free carrier indicates the contribution from trivial bands.
深圳是广东省了吗？
The free carrier dominance at the low energy range.
深圳是直辖市的这个 port.
Okay, and show a much stronger signal.
是直辖市.
The well point contribution shows the largest response below 0.5 eV. Overall, the contribution from K space near well points are smaller than 25% of the total dielectric function. And those are negligible above 1 eV. This indicates that the previous giant SAG probes in the IR and the visible range are resonantly enhanced by trivial bands instead of topological nature. To conclude what we have discussed above, firstly, broad optical dielectric function of tan-Marsden and Navi-Marsden are obtained by both ellipsometry and DFT. Two methods show a good agreement between each other. Secondly, large experimentally observed second harmonic generation are resonantly enhanced by trivial bands instead of well points. Thirdly, the dielectric function contributed by the K space near well points are smaller than 25% of the total dielectric function, and those contributions are negligible, especially about 1 eV. Finally, if you are interested in the content discussed above, please check the reference for further details, and thank you very much.